Let's see, who's missing?
Bill.
Okay.
Didn't Dave say you were passing an attendance sheet around?
Yes, yes. Thank you for reminding me. Would you start one and pass around? Put down your name and your call sign.
John, ARRL.org has a schedule for 2012 exams.
Yeah.
I was just checking it. Sometimes they're not always inclusive, but I tried. It's gonna take my
Feel like I'm ready.
Mm-hmm.
Feel like I'm ready for a test already.
Tell you what, when you're through, we're not even through yet. When you get through, man, you're going to be, honestly,
Cleared up so much, honestly.
when we get finished, I think you're going to find that the math part of this test is the easiest part of the test. You're going to say, man, I wish I had more math questions. Because we're going to discover that using simple techniques like this where you look at it, you can knock out so many wrong answers that you can pretty much just solve it. All right, everybody settle down. We're going to get started here. We've got a good bit more to go. Let's see here. I think everybody's in, so close this. Okay, continuing after the break. You've learned several techniques you can use now to eliminate impossible answers and get it down to some correct answers. And I've got some more tricks like that I'm going to teach you. And then we're going to go through some problems, and I think you're going to be able to knock them off almost like that without touching the calculator. But it would be wrong to teach you how to simply pass the test without being able to actually do some calculations here. So we're going to take a pause in our sort of logical thinking and go back and actually do a few calculations just so that get some brain cells going here so that in real life, if you have to actually do some calculations, you can do it. I'm going to teach it using what I will call the traditional method for solving these, the same one the book uses. If you want to use the rectangular to polar conversion functions on your calculator, that's perfectly fine. Nothing wrong with that, nothing illegal about it. If you're comfortable with that, that's fine. But I'm going to do the traditional way because I think it's a little clearer in terms of understanding what's going on, and also because that's the way all the books present it. If we've got an impedance, Z is equal to R, and we'll say plus JX, make that inductive, and we want to convert that to polar. Let's figure out, let's first talk about what the polar representation looks like. The polar representation has a certain impedance Z and an angle, that looks more like a less than sign. Hard to write an angle symbol. Angle, straight on the bottom, of theta. Let's review what we're talking about here. Let's take a point, a real point here. We're going to actually work this out here. We'll say Z is equal to 300 plus 400 J. We want to convert that into the polar form. We're going to do that the traditional way. So let me mark this out. 100, 200, 300, 400, 500. The same thing. We'll say 100, 200, 300, 400, 500. Let's first make a dot for this point on the paper. Resistance is 300. Go out 300. Inductance is 400 and it's positive, so go up here to 400. So this, make a point right here. What we want to do is convert from the rectangular coordinates into the corresponding polar coordinates. So we draw a line here, and we're going to need to figure out two things. We're going to need to figure out this angle, theta, and we're going to need to figure out this distance, which I will label, we'll call it Z. So those are the two things we've got to figure out here. We've got to go from this into this. Figure out. So we're trying to have to figure out what theta is and what Z is. Now, from what we just learned before the break, what do we know about the possible values of theta, given this being 300 and 400? Anybody can tell me what? Greater than 45. So if we calculate it and come up with an answer less than 45, we made a calculation mistake. It's got to be greater than 45 degrees. But we're going to actually calculate it out. We're going to go through the steps using calculator, because I didn't want you guys to feel like you wasted your money on your calculators. So I'm going to give you your money's worth here. We're actually going to do the calculations to solve this problem. Let's talk about how we do this. And this, again, is the traditional method. This angle theta is equal to the arctangent, which is written tan minus 1 of, and it's equal to the XL, we've got R, XL divided by R. Now they just have, I don't know any way to get by other than just memorizing that formula. That's simple trigonometry 101. I don't know how, this is a memory. This kind of thing I hate to have to memorize stuff, but do you have any memory trick on that one?
I do with cricket, believe it or not, and it was Oliver has a handful of apples for the senior cup team.
And how does that work there?
And it was opposite hypotenuse.
I can't remember that.
Well,
I can't.
This is the opposite. This is the adjacent, and this is the hypotenuse.
Yes, it is, but I don't
So if
understand.
you can remember that, and that's the part I always have trouble
okay.
remembering. So I do the process of elimination. I say, well, that's opposite because that's my angle, and all right, that's just an adjacent because it's nothing fancy. It's a straight line, and that must be the hypotenuse.
If that helps you do it.
Yeah, that's the problem with it. Is you have to know how to play cricket.
I don't. Okay, maybe that's my problem. Memorize this formula. So let's work it out. Everybody's got a calculator there. Get your calculators out. Get your brain in calculator mode. And we're going to plug these numbers in here. So XL is 400. So we've got 400. And R is 300. So someone who's got a calculator there.
I've come up with a better one. Oat. Opposite, adjacent, and tan.
Well, that sounds good. Okay. Oat, opposite, adjacent. Okay. Somebody, what's 400 over 300? 400 over 300. Somebody got the calculator. Okay, 1.333. All right, once you've got that, then we're going to do the second button and the tan button to get the tan minus 1. Tell me what the angle is. Let me get a calculator. All right, hold on. Let me get a calculator. All right, what was the answer again? 53.1. Theta is equal to 53.1 degrees. Is that right?
It's about 45.
Okay. So it is greater than 45. So we know we didn't make any horrifically bad mistake. You know, it's basically correct. I don't know whether 53.1 is right, but it's at least in the right ballpark. So that is how you calculate the theta. It's only a matter of doing one division and then one function, arctangent. That's all you have to do to calculate the theta. If you want to do it using a polar rectangular form, that's perfectly fine. But this is the traditional way of doing it, using arctangent. It's not hard. Now we got to figure out the distance here. And last week, when Robert was here, he remembered Pythagorean's formula. Does anyone remember Pythagorean's formula from last week? It had to do with a right triangle. If you have a right triangle that has an x, this is a right triangle, and a y, and we'll say r. Does anyone know how r is related to x and y? R squared is equal to x squared plus y squared. That is Pythagorean formula. Been around a long time.
If you remember the 1939 Wizard of Oz books, when the scarecrow gets his brain, that's what he recites.
Really? Wow. So you could be as smart as a scarecrow.
There you
They're still dumber than an 8th grader.
They're still dumber than an 8th grader, that's correct. An 8th grader wouldn't have taken this long to come up with that answer. 8th grader would have known that immediately.
But he's got to know how to play cricket.
He wouldn't know how to play cricket, that's right. Okay, now let's see here. Let me take this, and because we want to solve for R. Now this is where the 8th grade comes in, and I won't try to take you back to the 8th grade. If we've got R squared is equal to, we'll say R, let's make it Z squared. Z, because I'm saying Z is along here. If we've got, start over. Z squared is equal to R squared plus XL squared, and that's what we just came up with. That was Pythagorean's formula. Everybody okay with that so far? Because we got this side is R, this side is XL, so that's R squared plus XL squared is equal to the hypotenuse, the long side, which is Z squared. And here comes the 8th grade algebra that you've forgotten. We take the square root of both sides, and we come up with Z is equal to the square root of R squared plus XL squared. We went from there to there by taking the square root of both sides. Square root of Z squared is Z, square root of that is that. That's how we got that. If you can remember these two formulas, theta equals tangent minus 1 of XL over R, and you can remember this formula, the length of the magnitude of the impedance is equal to square root of the R squared plus reactance squared, then that's all you got to know to solve these problems. Let's solve it. We got to plug in here. Somebody get a calculator. R squared, so that would be 300 squared plus 400 squared, and then take the square root. Somebody work that out for us. Tell me what the answer is. I already know the answer. That's very good, Rick, very good. Another gold star issued today. Everyone work it out and see if you get 500. If you don't get 500, keep working on it. We'll help you along. But I want everybody to come up with an answer of 500. Keep working. If you need to, write it down. Square this.
500 is the impedance.
That's the magnitude of it. That's correct. The impedance is 500 with a certain angle. That's the way they polar. So 500 is a magnitude, and then we've got an angle. And the angle is, where it was, 53.1. Yes, the magnitude here, that is the length of the hypotenuse of this triangle here. That's what it is. So keep working, everybody. If we need, we'll do some help. We'll help you out if we need to. We want everybody to take the time and get 500 for an answer. Try writing it down. Take the 300, square it, and write it down on a piece of paper. Take the 400, square root it, write it down, add them up, and then take the square root. See if you can come up with 500. Once you get familiar with the calculator, you won't have to do any writing down, but if you need to, go ahead and write it down.
You can just take it in order. I mean, square root on this, and then plus. And
yeah,
the next
that's right.
Square.
That's correct. So we'll pause here and let everybody try to get 500 out of this. While you're trying to get 500 out, here's another trick that's going to help you pass the test. This relationship of 3, 4, 5 occurs several times in the questions. Whenever you see one side being 300 and the other side being 400, and they ask for the polar length, it's 500. Just remember 3, 4, 5. When you see a 300 and you see a 400, the answer is 500. Simple enough to remember, 3, 4, 5. It's always that. Now, even the other way around, suppose that we had 300 resistance and 400 reactance. If you turn these around and say we have 400 resistance and 300 reactance, it changes the angle. The angle is now less than 45, but the magnitude, the length of it is still 300 squared plus 400 squared, or 500. So regardless of the order of these, if you've got a 3 and a 4, the magnitude is 5. 3, 4, 5. So just look for problems that end up with 300 and 400 and immediately eliminate anything that doesn't have 500 for magnitude. If you can't remember 3, 4, 5, calculate it.
Hey, Phil?
Yes.
in case it helps anybody, don't be misled by the Excel mathematical nomenclature. It's just a triangle.
Yep.
You're solving for a triangle the same way you would do if it was on a farmer's field, or you're calculating how long a sloping antenna would be coming off the flagpole. That's all it is.
That's right. If we wanted to know how long a rope we needed to go from here up to the corner of the room, we would measure the distance along the floor there. We would measure the height along that wall, and we would apply this formula. Floor length squared plus the height of the wall squared, take the square root, and that's the length of a rope going directly from here up to there. Same formula applies. It's just, as Joe said, just solving a right triangle. How you doing, Laura? Getting close? Still not working on it?
Yeah, we'll still work.
All right, let's try it. Let's try it. What is 300 squared? Okay, see if you can get 300 squared and see what you come up with. 300 times 300, or you can square it. 300 times 300 equals. All right, and write down 9,000. 90,000, okay, excuse me, 90,000. And now square 400. 400 times 400. 160,000, okay. Got 160,000? All right, 160,000, 160, comma 000. Add those together, and what do you come up with? 90,000 plus 160,000. What'd you get?
250,000.
I'm sorry, 250,000?
Yes.
Okay, take the square root of that. 500. There you go. If you need to do it, if you need to write it down, do it.
Yeah.
Don't, if you get yourself confused by the calculators and trying to carry forward operations, just pause and say, hey, forget it. I'm just going to write it down step by step. Nothing wrong with that. You got plenty, they'll give you as much time as you want in this exam. Write it down, find 90,000, 160,000, multiply it up, write down 150,000, take a square root of that, come up with 500. Or remember 300, 400, 500, which occurs often on the exam. So now this is the traditional method of solving the problem. Let's do a capacitance because I don't want you to freak out if you're going down instead of up.
Will they typically always just use plus minus 90 degree range, or will they ever, sort of a trick?
No, it's all straightforward. Everything is straightforward. There are no tricks. Let's do this. Let's say we've got Z is equal to 400 minus J 300. And I recommend when you start working on a problem like this that you put a point on the grid that you made up here. So let's do it. We're going to go out 400. Yep. Going to go down 300. Remember, it's negative here, so we got 100, 200, 300, 400, 500. Go out 400. Yep. Go down 300. 1, 2, 3. Now, since we went out further than we went down, is the angle going to be larger or smaller than 45 degrees in magnitude? Smaller. That's correct. So the first thing you know is if you come up with an answer that has the angle that has a bigger magnitude than minus 45, it's wrong. It must be less than minus 45 degrees. It'll be somewhere between 0 and minus 45. Let's solve it out. Theta. Okay, in this case, we got to figure out let's draw the triangle here so we don't confuse ourselves. The formula in general is, and this is trigonometry, not necessarily electronics here. The trigonometric formula is the side opposite the angle. In other words, here's the angle, which one side is opposite, and this one's over here is opposite. And that happens to be XC, which is, in this case, 300. So it's 300. and divided by the side adjacent to the angle. Now, here's the angle, so the one adjacent to it is this one, which is 400. All right, someone divide 300 by 400. I think we know the answer to that, 0.75. And then do the arc tangent and tell me what the angle is.
36.86.
Sounds good. I believe that. 36.8. Okay, good enough for government work. 36.87 degrees. Is that less than 45 degrees? Yep. So we validated it. If we came up with a 60-degree angle, we know we're in trouble. So this sounds good. To make life simple here, we notice we've got 3 and 4. What is the magnitude? Got 300 and 400? 500. What? 500. Don't even bother calculating it. We know the magnitude. We've got 300 and 400. It's 500. So the answer is Z is equal to 500 and an angle of minus 36.87 degrees. That is the polar form of that point. Everyone understand how we did that? So there are only 2 things you have to learn here if you want to do it, the calculations using the formulas, and that is you have to know the arctangent formula, and it's always the side opposite the angle divided by the side adjacent to the angle. Tangent, just in general trigonometry, the tangent is equal to the side opposite divided by adjacent. Opposite over adjacent, tangent. And opposite, in this case, away from is XC. The one adjacent to, one touching it, is the R value here. Opposite divided by adjacent. And the magnitude, we use Pythagorean's formula. Square root of R squared plus X squared. How are we doing? That is, for that, you know, if you ever really needed to calculate a polar rectangular conversion, that's how you do it for an arbitrary value. I'm going to show you some more tricks to make it even easier on the exam, but you now know that you can always fall back and use these formulas for anything. I mean, even not just exam questions, but if you ever had in real life.
You have to work them in reverse.
Work them. I'm trying to think here. Yes, they do, and I think there are a couple, and we'll talk about that one. We'll do a reverse one. Might as well, using the formulas. Okay. Well, in that case, we were given these formulas are on the handout sheet, by the way. If you forget it, it's all written down on the handout, both ways, rectangular polar and polar rectangular. So let's go from a polar form where we have some impedance at some angle theta, and we want to convert that to a resistance plus or minus J times a reactance. So we've got the opposite problem. We've got to go the other way around from polar to rectangular. Okay, let's take a case here. We will say the resistance is, let's say, pick a number out of the air, 300. And we will say at an angle of, we'll say 30 degrees. Now it's 30 degrees, so here's our 45-degree line. So we have a length of 300 at 30 degrees. It's going to be a point somewhere in this ballpark. We don't know exactly where, but you can kind of eyeball it. You know, this, if you kind of imagine, sort of use your fingers as sort of a compass here, and go out 300 and sort of swing it up. The length of this line is 300, and at 30 degrees, just sort of eyeballing it, that looks about like 30 degrees. So it's somewhere close to that. I mean, a lot of times you can just sort of eyeball, just put a point as close as you can on your chart. That'll help you solve this problem, because now you immediately kind of know the answer is going to be resistance of close to 300. And you know kind of that the reactance is going to be, just eyeballing, like maybe 120, 140, 50, something like that. Just inspection. So we kind of know basically what to expect the answer to be. But how do we actually calculate it? Two simple formulas. X, let me make sure I get them right here. Who's got a handout for polar rectangular handy? Let's see, I want the corrected one, not the old one. Is this the corrected one? Okay.
I printed it.
Okay. To solve this, we've got two formulas. We've got XL and we've got R. And the formula is XL is equal to this magnitude times the, I don't think this is a corrected one, Laura. It should be this.
I printed out from your email.
I think you printed out maybe from the first one. Let me have the new one. That should be a sign. Yeah, the X is, but yes, okay. Yeah, it is. The XL, well, is equal to the sine of theta, and the R is equal to Z times the cosine of theta. Got two trigonometric functions there. So let's solve this. Someone figure out what the sine of 30 degrees is, please. Put in 30 and then punch the sine button.
0.5.
0.5. Good. So we know that the sine of theta is 0.5. So we have 300, which is the magnitude, times 0.5 is equal to 150. Everybody in agreement with that? The formula was the magnitude times the sine of theta. We looked up the sine of theta, calculated it. It turned out to be 0.5. So XL is half of 300, or 150. And that's kind of what we eyeballed over here, so that makes sense, right? Louis, you look a little confused, you okay?
Yeah, I just got lost somewhere.
Okay, well, let's try it. Let's take, would you calculate the sine of 30 degrees. Tell me what you come up with. Put in 30 and press the sine button.
My calculator got on red, so how do I change it back to degree?
Maybe you're in, okay. There should be a degree button.
0.5.
Did you get 0.5?
Yeah, I got a degree. I said just toggle, okay.
Okay. Okay, did you get 0.5?
0.5.
Okay. So 0.5 times 300 is 150.
Okay.
Does everyone got 150 there? So that is the XL. Now the R is 300 times the cosine of 30. So everyone put in 30, press the cosine button, and tell me what you come up with. Okay, we'll say 0.87. Multiply that times 300 and tell me what you come up with.
259 decimal 8.
259? 2.59 or 259? 259 ohms. So what's the rectangular? The resistance is 259 and something or another. And we have, it's a positive because we have inductance, so it's plus J150. So that is the conversion to rectangular from polar. And it required us knowing two formulas, this one with a sine and this one with cosine. Notice the formulas are exactly the same, except that one of them has sine and one has cosine. Other than that, they're the same.
I should have done this the other way around, because I then promptly wrote down the XL as the R.
Okay. Well, getting them backwards is a problem.
Yeah. Well, I realized, though, that I had it backwards.
Okay. Well,
the points put me above the 45.
Phil, just to emphasize, you're doing this just so they'll know the background.
that's correct.
In practical use, they usually will use the built-in rectangular polar function.
If you do. I often, because I'm just traditionalist, do it this way just because it's the way I've learned how to do it, and I can't remember how to do the polar rectangular. It depends on the calculator. I can do.
Well, and if you know it this way, you can do
Yeah.
it with the calculator.
Yeah, I mean, I could do sines and cosines in every single calculator, but the
Yeah.
rectangular polar is different depending on whether it's an RPN or a TI or a Casio or whatever. So I can always solve the problem this way.
What's that between the 300 and 4.5?
Okay, well, we took the sine of a sine of 30 degrees,
Yeah.
and we came up with 0.5. The sine.
So what's that between the, I got it to 300.
Oh, that's a star, meaning multiply. I'll put a dot here. Dot point times 0.5. 300 times 0.5.
Thank you.
150. And just to sort of check our work here, let's go back and what we've learned here. We've got an impedance of 250 with a reactance, a resistance of 250 with reactance of 150. Since the resistance is bigger than the reactance, we went out further than we went up. So what would we expect the angle to be? Lower than 45. And sure enough, 30 degrees is lower than 45. So you might want to check your work by just seeing if it's in the right ballpark. Is it less than or greater than 45? And if you got it, you know, if they don't match up, then you made some calculation. Maybe you've gotten these formulas backwards. You might have gotten sine, cosine mixed up. That would cause that to happen.
I think I would do them in reverse, so that, you know, because thinking about the formula, I always think the R first, plus or minus.
Whatever works for you. Whatever works for you. Okay, so now we've done rectangular to polar. We've done polar to rectangular using the traditional calculator method. And you are welcome to practice this if you prefer to use the rectangular polar rectangular button in your calculator. No problem. Go right ahead and do it. You know, nothing wrong with that. It's allowed on the exam. But I now want to go and give you a couple more tricks that are going to help you get through this test without having to do a lot of calculations. We've already learned several important ones. We've learned about the fact that if resistance is equal to reactance, the angle is always 45 degrees, plus or minus, depending on whether it's inductive or capacitive. We know that. We also know that if the resistance is greater than reactance, it's less than 45 degrees. And if reactance is greater than resistance, and make a mark on here, it's going to be greater than 45 degrees. Use this chart that you're going to draw on the scratch paper to help you solve these problems. Make points on it and look at them and eyeball them. And you can, a lot of times you come up with a close answer just from inspection of the chart. I got a couple other little tricks here to help you out here. We're going to see how many of these questions we can solve without using a calculator when we get through. That's our goal, is to see how many questions we can answer without ever touching a calculator. We know how to eliminate a lot of wrong answers by using the greater than or less than 45 degrees. We know how to eliminate a lot of things by knowing whether it's positive or negative. If it's inductive, it's going to be always positive angle. If it's a capacitive, it's always going to be a negative angle. Knock out anything that has the wrong sign. A couple of other tricks here. These are not complicated. If you, for some reason, forget these tricks, you can always fall back to using your calculator. But these are not complicated tricks. Let's suppose that we have a resistance R and some inductive reactance XL. And we're trying to calculate the angle theta and this magnitude here of impedance. Just from life experience, do you think Z is going to be greater than, less than, or equal to R plus XL? And to help you answer that question, I want you to imagine that you're out walking down the street and there's a park that you need to cross. And you can walk down the sidewalk here and then turn the corner and walk down the sidewalk there, or you can walk diagonally across the park. Which path is shorter? Diagonal. 5-year-olds understand at some level that walking diagonally across a park is a shorter path than walking down the sidewalk, turning the corner, and walking down the other. Does that kind of intuitively, if life experience makes sense? Now what that tells us is that Z is less than R plus XL. Anybody have any problems with that? Questions about it? If you ever come up with something, if you ever, have a problem where they present something and Z, the magnitude of this polar, is greater than the sum of the two sides, can't be right. It can't be right. It's got to be less than the two sides.
And this was an impedance.
It's for light. It's for anything. This is for distance across the park. So it's for impedance. Yeah, if you're going from rectangular to polar. So it'd be something like this. They're going to give us a problem like this. They're going to say that we start out with a rectangular of, 300, we already know the answer to this because 3, 4, 5. But it'd be something, something more difficult than that. And there'll be several choices. And let's say one of the answers would be something like 350. No, that's not a good choice. Let's see here. What we want here, greater than the longest. So be something like 700. Let's make it 900. 900 with some angle. Well, we know that if we're walking down a park and we walk 300 feet, turn the corner and walk 400 feet, we've walked a total of 700 feet. If we're cutting diagonally across the park, surely we're going less than 700 feet. So the magnitude diagonally has to be less than 700. 900 is not less than 700, not a possible answer. The answer, the distance, has to be less than the sum of the two. Are you with me on this? I mean, you can always work it out. If you don't remember this stuff, you get confused by it, then don't worry about it. Just use your calculators and work it out. But we're going to see a lot of these problems by using simple things like that, just thinking, wait a second, it's got to be less than the sum of the two because we're going on a diagonal, and you can get the answer. The other thing we notice is that it has to be greater than whichever one of these is the larger one. And again, this is walking across the park kind of thing. If we got a park here, and this is 300 feet long, and this is 400 feet long, we walk diagonally across it, we're walking more than 400 feet. If we walk from here to here, it'd be 400 feet. Since we're starting back here, it must be more than 400. Flip it around, make this be 400 and this 300. It's still got to be more than 400. Because we're walking, even if we could start up here, it'd be 400. But we got to go up and over. So it's got to be, so the magnitude has got to be larger than the largest of the two. It could be, it's got to be larger than the resistance or the reactance, whichever's the larger one. It's got to be larger than either one of them independently. But it's got to be less than the sum of the two. Otherwise, it'd be like walking all the way around and assuming that was the same as the diagonal. Got it so far? Does that kind of make logical sense just from life experience? But if you can't remember it, just fall back and work it out. Is any confusion about what I've explained here? Just think about walking across a park. That the diagonal is less than the sum and it's greater than whichever one of these is larger. You can eliminate a lot of false answers by simply using that. And that's just, yes?
I wanted to mention, you already mentioned this, I wanted to underscore it. If you use polar rectangular function on your calculator, practice it beforehand. Do not go in there with another type of calculator because calculators all differ. Sometimes they get y back first and x, sometimes the angles and the magnitude, and if you get confused, you don't want to get confused.
Absolutely, absolutely. And if you do calculate it, try to also apply these things to check your answer. If you do a calculation of this and convert it to polar and come up with 900, say, uh-oh, I got a problem here. That's greater than some of these two. Or if you do the calculation, come up with, this thing, and we come up with, we only have to walk 200 feet. No, can't be. We just know it's got to be more than 400. So that is going to eliminate a lot of false answers right there by knowing that it has to be greater than the largest one and it has to be less than the sum of the two. I'm going to give you one other thing which will eliminate a couple more answers, and that is, don't ask me to explain this, but this length, we'll call Z, is actually less than 1.5 times the largest. If you can't remember that, this, I don't want to make this harder. I want to make this life simpler. So if you can't remember this, you just forget what I'm saying here. In other words, whichever of these is larger, multiply by 1.5, and this has to be less than that. So this 400 is larger. What's 1.5 times 400? 600. Has to be less than 600. In fact, we know the answer. If it's 300 and 400 is 500. Is that less than 600? Yes.
Greater than 400.
That's correct. So we know it has to be greater than 400 and less than 600. So if you can just remember this, it's less than 1.5 times whichever one's larger, and greater than the larger one. So it's greater than the larger one, but less than 1.5 times the larger one, and less than the sum of the two. You're going to be surprised how many problems you're going to get. You'll just inspect the answers. Can't be. We'll see. We're going to go through some of these things. How are we doing? Everybody, how's everybody with me? You with me so far? Okay, now it's time to actually do some of the practice problems and see how we can apply all this stuff to it. So everyone pull out your practice exam questions. And let's apply this and see how much we understand. Okay, we're going to skip, for the time being, time constants and get right into, skip up to phase angle. This would be question E5B09. E5B09, phase angle. Everyone find E5B09. And we will work from that point forward. Okay. Yeah, the exam questions. Can you find E5, B09? There you go. Yep, phase angle. Different printout. I don't know where.
I've got the older.
Okay.
Oh, you printed them out again?
Yeah. Everyone working your way around to E5B09. It's just first question under phase angle section. Phase angle, E5B09. What is the relationship between the current through and the voltage across a capacitor? Eli, the Iceman, comes through. It's a capacitor. Look up here, and we see that current leads voltage, voltage lags current. So we got to find out. Okay, so voltage, current leads voltage. Current is in front of voltage by 90 degrees. There's always a 90-degree phase shift across the inductor capacitor. So boom, got the answer to that one, no calculator. Next one, E5B10. What is the relationship with the current through an inductor and the voltage across the inductor? Good old Eli comes to the rescue again. Current through, so we know that voltage leads current. Voltage leads current by 90 degrees. All we had to do was look at good old Eli, and we got the answer to that question. Now we come down to E5B07, complex impedance. Now this is where everybody freaks out on the test, but we're going to see how easy these are now that you've learned all the tricks we've come up with. What is the phase angle between the voltage across and the current through a series RLC circuit if XC is 500, R is 1 kilo ohm, and XL is 250 ohms? Here we go. Let's work this out. We'll start out doing it tediously, writing things down, but as we progress, you're going to discover you can be able to do these things very rapidly in your head. So what do we got? We got three things in series. We have three things in series. What do we do to calculate the total impedance? We add them together. So let's write it down. We've got an XC of 500 ohms. So we've got, for that first one, we've got zero resistance. It's a capacitance. What is the sign? It's negative. 0 minus J, and what's this magnitude? 500. Okay, what's the next thing in series? is a resistor of 1,000. So that's 1,000 plus J0. There's no reactance. And what is the last thing? XL is 250. So that's no resistance. And it's an inductor, so that's plus J250. Everyone with me so far? I'm writing this down. We're going to add them together because they're in series. We had, I'm sorry, this is 1,000. So what's the total resistance? 1,000. Remember, there's only one resistor, and there's one, that's nothing else. We add these, we've got minus 500 plus 250. What's the total reactance? Minus 250. Minus J250. Make sure you get the sign right. So we got 1,000 minus 250J. First thing, is the angle going to be positive or negative? Negative. Do we have, what do we have here? Let's see. Oh, okay, they made it tricky. They said leading or lagging. Okay, well, let's see here. We've got a minus value, so we have to go back to Eli and the Iceman. If it's ice, what do we know about the current voltage relationship? I know this is negative, remember? Negative here, so negative here. Current is leading the voltage. Let's see what are our choices here. Okay, voltage, they phrase it the lagging way. Okay, so voltage is lagging current. So let's see which ones here. We've got voltage lag. Notice there are 2 leading and 2 that have voltage lagging. See that? Eliminate immediately the ones that have voltage leading. A and B are gone. ICE told us that. So we didn't do any calculation. We just eliminated 2 of the answers. Now, let's see here. Let's look at this logically. We're going over 1,000 on the resistance. We're going up 250, or actually down, excuse me. It's less than 45. That's correct. I'm going over 1,000, going down 250. So the angle is negative, but less than 45 degrees. So what does that give us to? C. C is 14 degrees, less than 45. Anybody need a calculator for that? Okay. See how easy this is? Here's a clue, by the way, a hint. 14 degrees shows up in a number of these. Anytime they give you 14 degrees, that's the right answer. They may, for those who are maybe watching this tape in the future, they may change that in the next exam. So don't. That's not. They'll probably monitoring this room and going to change it so 14 is always the wrong answer in the next exam. But at the current time, 14 is always the right answer. Now there are some questions which have 14.
Leading and lagging.
Yeah, that's right. It'll have 14 on more than 2 answers, so you got to figure out which one's right. But whenever you see 14, it's got to be one of those answers every single time, guaranteed.
If you have the Iceman written down, that should be easy to figure out.
Yeah, that's easy to figure out. So whenever you see 14, it's the right answer, but then you have to figure out which one it is, eliminate the other one. Okay. All right.
You said this was a minus sign,
Yes, because it's capacitive.
right?
And so since it's a minus sign where the angle
Right.
is a negative angle,
Okay, then you're gonna use that.
which one's negative up here? Remember? Okay, remember,
Current leads the voltage in a capacitor,
that's correct.
okay?
Which means voltage,
lagging, so that should be right.
which means if current is leading the voltage, voltage is lagging the current.
Oh, the voltage there.
See,
Yeah,
they
that's
tried
what you have to
to
watch
they
out for.
tried to trick you.
Either I'm in front of you
Yep,
or you're behind
that's
me.
right.
One
You've got to watch it. They're going to try to trick you.
But that voltage is what I was thinking.
They're going to try to trick you, and you have to look. Be careful whether it's leading or lagging, and always, that's why you want to look at this thing here and think about it, leading and lagging, because it could be either specified either way. So be careful about leading and lagging, which one's which. Mm-hmm. The next problem, this would be B08. What is the phase angle between the voltage across the current through a series or LC series? Okay, XC. All right, let's see. Where's my eraser? As we go along here, I'm going to make fewer write less because I think you're going to see this is really simple stuff here.
Actually, anytime you see XC greater than XL,
Yeah, that's right, Gene. You got it.
then you've got the lead.
That's correct. That's correct. All right, so first place we see was only one resistor is 100 ohms, the thing, right? Mm-hmm. So we know the resistance is 100. And we've got XC. XC is minus. Everybody agree on that? C. We've got of 100. We've got XL, which is positive, of 75. So if you say minus 100 plus 75, what's that? Minus 25. Minus 25J. So that's what it is. We didn't even have to, we just did it in our head. Can everybody agree with this? 100 minus 25J. Minus 25J is an inductive or capacitive net? Capacitive. Okay, we look up here. So let's see what are our answers here. So the first thing we see is that, we've got to be careful with the leading and lagging. And they say, okay, so they want the voltage. So voltage is lagging current. Okay, so eliminate anything which says voltage is a leading current. So we're down to voltage is lagging current. Now I've got, okay, so voltage is, now let's see, next thing we're going to draw a little chart here. We're going out 100, we're going down 25, and in fact, there's a 14 degrees here, 14 degrees. So immediately say home in the 14 degrees. So it's 14 degrees, and then we just have to look at the leading and lagging. Got the minus, so the voltage is lagging, correct? A is the correct answer. Everybody got that? Everybody used the calculator so far, right? Okay. Next one. What is the phase angle between the voltage across the current through an RLC circuit? If XC is 25, R is 100, and XL is 50. All right. Here we go. What is the total resistance? Resistance is 100. What is the total reactance? We've got a minus 25 and a plus 50. Plus 25. Everybody understand it's plus 25? Plus 25. I'm supposed J25. So what do we know? It's plus, that means it is inductive. If it's inductive, good old Eli is going to give us the answer here. That means voltage is leading the current. E in front of I, voltage is leading current. And, we see 14s. 14s are good. 14 degrees with voltages leading the current, B is the answer. Got it? All right, we'll do a couple more here. I think are you getting the idea here? I mean, how simple can you be, right? Let's see, we'll do a few more here, but I think you're beginning to get the idea here about how simple this stuff really is once you figure it out. Okay, let's see what we did. Which one did we do? What are we up to? Number 12? B12? Yeah. Or B12. Phase angle between the voltage. Okay. R is 100. And what is the net reactance we've got? XC is minus 75. XL is, okay, so minus 25. Minus 25, or J minus J25. Okay, so we know it's negative. That means it's capacitive, which means that the voltage is lagging the current. Voltage is lagging the current. 14 degrees. 14 degrees, voltage lagging the current must be C. Got it? All right, let's see here. Oh, here's one that doesn't have, no, we still have 14 in that one. Let's see, let me try to find one that's a little bit harder. Here's a good one. Go up to E5C01, E50C01. It's another good one you're going to be able to solve here. All right, E5C01. So what is the resistance? Is 100, right? And what have we got for reactance? We've just got a 100 ohm reactance inductor. Is an inductor positive or negative? Inductor is Eli, that's positive, plus J, 100. 100 and 100. What do we know about the angle if these are the same?
45 degrees.
Okay. So the angle's got to be 45 degrees. So let's see here. Are there any 40? There sure are. There's only one that has 45 degrees. So that's supposed to be the answer B. That's a simple, isn't that trivial? You just should look at these things. Next one. In polar coordinates, what is the impedance of a networking system? Okay, let's work this one. 100 over, okay. All connected in series. Let's work this out. This is another fun one. Okay, what is the resistance? Let's see here. Wait, hold on. Which one am I on here? C02?
C02.
Okay, C02. What is the resistance? 100 ohms. And let's see, what is the net reactance? We've got a 100 ohm inductor and a 100 ohm capacitor. So what is the net reactance?
Cancel each other out.
They cancel each other.
Zero.
So it's plus J0. And by the way, that means we've got a resonant circuit, if you remember that part we talked about. Now, if we go back to the plot here, if all we have is a resistance, where is the point got to fall?
On the line.
On this line. Which means, what is the angle got to be?
0 degrees.
0 degrees. It's not going at a pole. It's on this line. So there's no tilt up or down from the. So we know it must be 0 degrees. So we've got two choices here. Now let's look at here. So we've got possible answers of B or D. Both of them have 0 degrees. So we've got to figure out which one it is. Scratch our heads here a little bit. Well, we had a resistance of 100. We got two possible answers: 10 ohms or 100 ohms. Well,
The first two cancel out.
you know, we've got a resistance of 100 along here, so it's got to be 100. I mean, it's just the line is just out to 100. It's just the point 100, so the distance is 100. Just like we were talking about before. Okay, so we got that one down. In polar coordinates, what is a piece of network consists of 300 ohm reactance capacitor, 600 ohm reactance inductor, 400. Okay, here we go. Let's work this out. All right, let's see here. We got what's our resistance? I always like to start with the resistance, 400. And what is our total reactance? We've got plus 600 minus 300. Got that? So that would be plus 300. Plus 300 plus J300. There you are. Anybody see a 3, 4, 5 show up? 3, 4. So what is the answer going to be here? It's got to be 500. It's got to be A. Are you guys getting this? This is just simple or what? Yeah. This is like to be the easiest part of the exam by the time we're through this. You're going to go in there and say, oh, yeah. Everybody else is going to be there ferociously calculating. You're looking around all your colleagues there. They're going to be doing all this.
What you're saying is that we'll fail on the other part and they'll fail on this.
Yes, that's exactly correct. Because you're going to be so confident. You're so confident you're going to forget about all the rest of the exam, okay? But you're going to be in there doing all these calculations. Oh, everybody else is going to do the calculations. And you're going to be saying, and so the monitor in the back of the room is going to be watching everybody. Everybody's supposed to calculate, and you're doing. So they're going to come over and start looking over your shoulder, you know, to see where you're getting these answers. You must have it secretly written on the back of your hand or someplace.
Make the questions on the bands even
That's
worse.
right. You know. Okay, the number C4. In polar coordinates, wasn't P of network and 400 ohm reactance. Okay, I immediately see 300 and 400. Everybody see 300 and 400? Okay, so we know the answer is be 500. Wait a second here. 400, where's D? Oh, we got two 500s. Okay, we got two 500s to choose from. So we got it down to 2. Now let's think here. Let's write it down. We have to think a little bit more on this one. So we've got a resistor of 300, and we've got a capacitor. That's minus J of, what is it? I'm sorry. No, I'm sorry, I got it wrong. It's 400 ohm resistor, right?
Right now.
What? 400 resistance?
No, 300 resistors.
Okay, yeah, 300, okay. Minus 400.
Capacitor.
Okay, so we know it's capacitance. Okay. So we immediately know that it's got to be 500.
Negative.
Okay, yeah, but negative, and we know, that's right, very good, Gene. We know there's a negative angle.
Capacitor.
So what do we got that has 500 with a negative angle? Only D.
45 degrees.
Only D. Boom. There's the answer. Okay, now we come to one which is actually hard. I hate the parallel ones. I hope you don't get parallel ones on your exam. They are harder to do, much harder to do than the series ones. But we're gonna face the challenge of dealing with a parallel. We started out learning that in series we had ZT is equal to Z1 plus Z2 plus Z3 and so forth. We just added up the impedance. Life was simple. Life was good. You hope you only get serious problems on your exam. When you get to parallel, life gets more complex. What it is ZT 1 over ZT is equal to 1 over Z1 plus 1 over Z2 plus 1 over Z3. That's the form. Basically, we have to convert these into how well they pass. So what we've got here is a circuit that has, let's take a look at this one. This has a inductor in series with resistors. We've got a resistor, and in parallel with it, we've got an inductor. So that's our circuit. The resistor is 400 ohms. And what is our inductor is 300 ohms. Okay. Now this is harder because these are in parallel. So be careful when you see these problems. Are they serious? You know, if you get in a roll here, doing them over and over again, then all of a sudden they say parallel instead of series, and you miss that, you're screwed. So be sure to check which one it is. Okay, let's try to work this thing out here. See if I can get this right. It's been a while since I've done parallel. What we do is we have to convert impedances into what are called admittances. If an impedance is something which impedes or reduces, makes it harder for something to flow through, impedes it, an admittance makes it easier for something to flow through. So as we increase impedance, it becomes progressively harder to make it through the impedance. As we increase admittance, it makes it easier to make it through. Admittance is like, welcome, come on in. Okay, that's what admittance is. It's the opposite of impedance. So we're going to convert these into admittances here. And let's try to do this. So we've got a 400 ohm reactance inductor with 300 ohm. Okay, so we're going to have 1 over 400. And this was an inductor, so we're going to have plus 1 over 300. Okay, let's work this out. Use your calculators. 100 over 400. 400 inverse. I come up with 0.0025. All right, 0.0025. Okay, 1 over 300. 1 divided by 300. I come up with 0.0033. Everybody got that? All right, let's add these together. I come up with 8. 3 plus 2 is 5. 0.00. I come up with 0.0058. Right. How's that sound? All right, so let's now, we've got 1 over ZT equals that. So now we need to take the inverse of that, 0.0058. Take the inverse, and I come up with 172. Everybody agree with me, 172? All right, let's see how we're doing here. Okay, let's see here. Okay, 400, 300. Well, we don't have 172. Where did I go wrong here?
When React, we got the numbers backwards. It's a 400 ohm reactor.
Oh, it's a 400. Well, still, it should be the same though. 400 and 300. Okay, well, let's see here. Let's look what they do. Who's got a book handy? Let's work this out. We'll follow their example here. Somewhere I skipped the track on this.
423.
Oh, I see. Because we need to go to we need to go to polar. Okay, they made it even. This is frankly a hard question, but don't worry, we're on top of it here. So we need now to go to polar. Well, let's now think about what we've got here. In fact, I'm going to, just to make sure I don't screw this up, I'm going to sort of follow through in the book here, which is on page 404. Well, except it's the admittance, so we have to go to admittance. Okay, that was solved on page 4-23. And I'm just going to follow through the book. We'll work it out as they do it in the book. Make sure we don't screw this thing up here. Okay, let's see here. Here we go. So we did the first step. We got the 0.03 and 0.025. So that's okay. Use 3 to add the admittance together. We did that, and we got 0.005. Well, actually, what they want to do is add them together without and write it down as a complex admittance. So let's do that. Rather than doing this, what we're going to do is write it down as a complex admittance. That's pretty mind twisting. A complex admittance. but it's similar to a complex impedance. It's just that it's an admittance instead of an impedance. And the symbol for admittance, complex admittance, is Y. Remember we had Z for complex impedance. Y is used for complex admittance. And what have we got here? Well, first we inverted the resistance. Well, 1 over 400 was 0.0025. So that's 0.0025. And the unit for that is a Siemens, is the actual unit for that. Now, we've got the reactance. Here is the interesting twist on this. In addition to inverting the value, when you go from impedance to admittance with a reactive component, you flip the sign. So the admittance here, this was an inductor, which would be plus. We want this to be, we flip the sign, a minus J, and then the 1 over it was 0.0033. So let's refresh our memory how we got here. We got here, we had a 400 ohm resistor. We did the inverse of that, and that's how we got the 0.0025. Follow that? We have a 300 ohm inductor. We inverted that, and we got 0.0033. That's where the value, the magnitude came from. Where did the sign come from? An inductor is positive, but when we compute it...
You're going to need to flip those because it's minus 0.0025.
Oh, did I do it?
Yeah, that's where that will matter.
Okay. Okay, well, which one, let's see, what's 1 over 400?
The 400 is the inductor.
Is the what?
You
got those.
the resistance.
Oh, I wrote them down backwards.
Yeah.
No wonder I got them backwards. Okay, sorry. So the resistor was 300, is that it? Yeah, okay. And the inductor was 400. Okay, I'm sorry. Let's start over again. So 1 over 300 was 0.0033. So let's correct this. Let me do this all again here. Write this down again. So what is the admittance from the resistor? That's 1 over 300, 0.0033. With me so far? Mm-hmm. And we had 400. The inverse of 400 was 0.0025. The inductor was positive. We went to admittance. We flipped the sign and get negative. So that's minus 0.0025 with a J out here. With me so far? That is the complex admittance. Okay. Now, convert the admittance back to impedance. So what we have to do now is, let's see, we need to now go to polar. Write the total admittance in polar form. All righty. They're making us work hard here. Let's draw this out. We've got here, well, what we have to do here is we have to figure out the magnitude. Remember the old Pythagorean formula of the, R squared plus XL squared. Okay, I think that still works here. Let's see, let's try that. Let's see, what do we get for that if we do these two together? What do we got here? For 0.0033 squared plus 0.0025 squared equals that. Let me see, take the square root of that, we'll come up with. I come up with 0.004. Okay, 414. Okay, so here we go. Let's plug these numbers in. What we've got is the square root of, we take the R squared, that's 0.0033, and we square it. We take the XL, which is 0.0025 squared. And we add them, square those two, add them together, take the square root, and see what you come up with here for an answer. Close. not exact, close. It should be 00414. Try it out again. Do this. 0033 squared plus 0025 squared, and then take square root. You should come out with 00414.
Bill,
Yes.
I need to stop and change batteries.
Yes. Go ahead.